DC circuit, we talked also about KVL, KCL, and we talked about complex powers, which you should be familiar with this: real power, reactive power, apparent power, power factor angle, all of these stuff. So in today's lecture, we will focus on how to use the AC in real applications. So we talked about the complex power, which is denoted by S bar, is equal to P plus JQ. This one in rectangular format, such that P is the real power, Q is the reactive power. And it can be written in polar format, which is S angle theta, such that S is called apparent power, theta is the power factor angle. The units of P is watts, units of Q is var, and var means volt ampere reactive. The unit of S is volt ampere. The unit of theta is degrees. The unit of S bar, which is volt ampere. So you need to know all of these units associated with each element, and you need to know what do I mean by S bar? What's the difference between S bar and S? What's the difference between P and Q? And also, we talked about S bar equal to V times I conjugates. And the conjugate, we said that if I assume I is I angle beta, then the conjugate means negative angle. Or not negative angle, means reverse the sign of the angle. If the angle is negative, make it positive. If the angle is positive, make it negative. Just reverse the sign of the angle. So it's V angle I. So V times V bar times I bar conjugate. So it's going to be V angle alpha times I angle beta, all conjugates. Then it's going to be VI angle alpha minus beta. This is equivalent to S angle theta. So based on that, we can say S equal V times I as the magnitudes. There is no bars, which means it's magnitude. No complex quantity. And theta will be alpha minus beta. So in theta, we denoted this by called power factor angle. And in last lecture, we focused on the definition of P, definition of Q, definition of S. And we went to Tillinger's theorem, to how to apply Tillinger's theorem on that. Now, in today's lecture, we will focus into theta, or the power factor angle. So there is a definition that's very useful in applications, which is called power factor, which is related to the angle. So we said theta is power factor angle. So the power factor is cosine of theta, cosine alpha minus beta, or cosine of theta. This is called power factor. And power factor also, it can be denoted as, since we know S equal P JQ and S angle theta, we can say that's P equal to S cosine theta. Then we can say PS times, since cosine theta is power factor, times power factor. Therefore, power factor will be P over S. So we have different formulas for power factor. We can use the real power and apparent power. Note that S is apparent power. It's not S bar, it's S, which means apparent power, not the complex power. Again, you need to distinguish between the complex quantity and the magnitude quantity. How can I distinguish? If there is a bar, this is the complex quantity. If there is no bar, this is the magnitude. So, based on that, we can say that power factor, we denoted by PF equal to P over S, or cosine alpha minus beta, or the same as cosine of theta, such that alpha is the angle of currents, angle of voltage, beta is the angle of currents. Or we can say cosine of the power factor angle. Okay, so why we are using this? Or what's the indication of the power factor? What's the meaning behind the power factor. So by looking at the power factor formula, it's P over S. So what's P? The physical meaning of P is real power. What's the physical meaning of S? Apparent power. What does this mean? Let's refer to last lecture. Let's recall last lecture when we talked about chips. There was an image of lace chips. So we said that the apparent power is the whole bag of chips. The real power is the actual chips inside the bag. And the reactive power is the air that's inside the chips to keep it fresh. And we mentioned that we couldn't make a 100% full bag of chips. So we need to keep the chips fresh, and we need to make it the chips as much as possible. So the power factor is the percentage of the actual chips from the whole bag, which is the something that you eat, the percentage of something that you eat with respect to the whole bag or the useful thing. So what's the percentage? If let's assume that the percentage is 90%, then I have good chips, which is filled a lot with this bag has a lot of chips. But so if the power factor is 50%, which means it's just half of this bag is filled, which is kind of, we can sometimes accept it, sometimes poor. How about if the power factor is 10%? So I'm buying nothing. I'm buying just few chips. So that's how we imagine it. So the desire to be as high as possible. But again, we cannot, in real life, in real application, we cannot make it 100%. We cannot make full bag of chips with no air or with no gaps at all. We cannot make that. So most likely the power factor should be within 90s, 98s, 96, 92, 90s. That's the acceptable way. There should be some range on that depending on the criteria or depending on the utility conditions, but it should be within this in 90s. How about if it's in 80s? It's sometimes good, sometimes we need to improve it. We need to increase it. So we can determine if it is good or not by looking at the power factor, how my system is good or not. Okay, someone can say, what's this? How this will affect into my power system? Let's assume that you want to consume or you want to eat, for example, 100 chips or 100 chip slices. So if each chips containing 10 pieces, then you need 10 bags, right? If each chips has 50 pieces, then you're consuming 2 bags, right? For the same amount, 100 pieces, you need 100 pieces. You can consume, if it is the power, if the each bag containing 10, then you are consuming 10 bags, or you need 10 bags. If you need, or if each bag containing 50 pieces, then you need 2 bags. For the same price, the same size. So what's the cheapest? Of course, 2 bags. The chips or the bag that has higher amount of pieces. Or the cheapest is the higher power factor. When the power factor is low, then I will pay more. I need to pay more. Or I need high energy. A lot of energy will go as waste or will go as reactive power. So sometimes I need to improve it. I need to increase it. So here is the definition of the power factor is indication how my system behavior is good, how I'm consuming the power. And you need to distinguish between the power factor and the efficiency. The efficiency is related to the losses, while the power factor is related to how the energy being divided between real and reactive power, useful energy or reactive power. So there are some cases associated with power factor. There's something called lead power factor, lagging power factor, and we have something else called unity power factor. Most likely, let's look at the angle of the power factor angle, theta. So if theta is positive, then it is lag. If theta is negative, then it's lead. If theta equal to 0, then it's unity power factor, or sometimes we call it UPF. So there are three cases associated with the power factor. Let's assume that we have the angle, or we have power factor equal 0.8. We know that the power factor equal cosine theta. So I can have theta will be cosine inverse of 0.8. By put this into the calculator will give you 36.87. But is this the only solution? 36.7, 0.87 degrees. This is not the only solution. Why? Let's recall the four quadrants. That in the first quadrant, all are positive. Sine is positive, cosine is positive. In the second quadrant, the cosine is positive, the sine is negative. In the third quadrant, both are negative. And in this fourth quadrant, cosine is negative and sine is positive. And let's recall that we know that the cosine is even function. What do I mean by even function? When I say cosine negative x equal to cosine x equal so and so on. So in other words, when I say cosine 36.87 degrees, it will be the same as cosine negative 36.87 degrees, which will be 0.8. When you substitute these two values, they should be what? Give 0.8. So when I make the cosine inverse, I have two values. So it can be either positive or negative. Again, the positive means lead, the negative means lag. Right? So I have at 0.8, I have in this side which is lag, and this side is just lead. I think, yeah, one's positive lag, one's negative lead. So for any values for the angles of the power factor angle, there should be two ways, positive or negative. So which is lead or lag. So when I say the power factor equal 0.8 for a certain system, is this enough? Just by saying power factor 0.8? No, it's not enough. Why? When I make the cosine inverse, I will have two values. So that when the power factor is lag and the power factor is lead, they are two different systems and very different systems. How can I distinguish, or how can I know this? There should be an information given with the equation or given with the system. So I need to say power factor equal 0.8, and I need to determine is it leading or lagging. There should be mention in the question. So let's assume that I'm giving you the power factor equal 0.9. That's not enough. You should say there's something wrong. Is it leading or lagging? It must be determined with the question. Otherwise, there will be missing information. So you will see 0.8 and it's lagging. Then I can realize 0.8, the cosine inverse 0.8, 36.87. Since it's lagging, then it's positive. If the question says the power factor is 0.8 but it's leading, then I'm gonna to find the angle, I'm gonna say cosine inverse of 0.8. Then it will be 36.87. Since it's leading, then I'm gonna insert negative sign. Okay? So when I say 0.8 and lagging, then theta will be 36.87 and it is positive. When I say power factor equal 0.8 and leading, then theta will be negative 36.87. That's how we figure out. That's why there must be defined. Any questions? Now, how to find the power factor for the voltage source and the current source? You need, if you have a voltage source, you need to find the currents. So by knowing the angle of the voltages, the angle of the currents, we can find the power factor angle, which is alpha minus beta. Then find the power factor cosine of this angle. How about the other elements, circuit elements, resistor, inductor, capacitor? The same way, you need to find the voltage or the currents. But there's a shortcut. So which is, we can find it easy. Determine the inductive power factor. So we need to know the voltage of the currents and the angle of the currents and the voltages. So the voltages is V angle alpha. The currents, I, according to Ohm's law, will be V over Z, which will be V angle alpha over JXL. And we know 1 over J equal to negative J, which will be 1 angle negative 90 degrees. So it's going to be V over XL angle negative 90 degrees. I'm sorry, alpha minus negative 90 degrees. Therefore, we can say beta will be alpha minus negative 90 degrees. Then theta will be alpha minus beta. Then it will be alpha minus 90 degrees, which will be 90 degrees. So theta here is positive. This means what? Lag or lead? Lag. Right. So this means lag. How about the capacitor? The capacitor, the same way, I equal V over Z, which will be V angle alpha over minus JXC. Then it's going to be V over XC angle alpha plus 90 degrees. 1 over J, 1 over negative J equal to J, and J equal 1 angle 90 degrees. That's why it's positive. So we can say beta equal to alpha plus 90 degrees. Therefore, theta will be alpha minus beta, which will be alpha minus alpha plus 90 degrees, and the negative sign will be on the negative 90. So it will be negative 90 degrees, which means negative. So the capacitor will be what? Leading. How about the resistor? Let's assume Z bar equal to R. Then V or I will be V over R, which will be V angle alpha over R angle 0, which will be V over R angle alpha. Therefore, beta equal to alpha, then theta equal alpha minus beta, which will be 0. This means unity power factor, or UPF. The unity power factor does not have lead or lag. It's just unity power factor. This is the only way that we didn't have leading or lagging. Based on that, we can conclude this. At any inductor, every time it's lagging, any capacitor, every time it's leading, any resistor, every time is unity power factor. Take it as a rule. How about if there was a combination between resistor and inductor, the load will be trending to be in the, lagging. How about if the system is a combination between resistor, inductor, capacitor, then it might be leading, it might be lagging, depending on where I'm observing. Where is the point of observing? Okay? Is that clear? Any questions? So you need to know now the difference between leading and lagging. And you need to know or memorize this. The inductor, every time, lagging. The alone, standalone. The capacitor, standalone, is leading. The resistor, standalone, is unity power factor. Okay? Let's see a quick example about the power factor. Okay. Okay, from last lecture. In last lecture, there were two examples associated with the diligence theorem. So there was example number 1, example number 2. So in this question, find the power factor for the source. By going back to that question, we will realize that the angle of the voltage source was 0, and the angle of the current associated with the voltage source, it will be negative 15, 26 degrees. That was an example 1. So how can I find the power factor? So you can go back to the last example, example 1 in last lecture, and just add another point, which is find the power factor of the source. How can I find the power factor of the source? What's the power factor formula? Cosine theta, right? What's theta? Alpha minus beta, cosine of alpha minus beta. So it will be cosine of alpha is 0 minus beta minus negative 15, 26 degrees. So the answer will be 0.965. Now, this is not enough. I need to determine, is it leading or lagging? What do you think, guys? Is it leading or lagging?
Lagging.
Lagging, by looking at the sign of the angle. The sign of the angle, 0 minus minus plus. So it will be positive. That's why it's lagging. Okay? That's it. That's how I find the power factor. It's just easy topic. Just as an extension for, you can add this extension for the last example. Okay, example number 2, in last lecture as well. So the angle of the voltage source was 0. The angle of the current associated with the voltage source was negative 30.96 degrees. How can I find the power factor? So power factor, cosine of theta, which is cosine of alpha minus beta, which will be cosine of 0 minus negative 30.96 degrees, and it's going to be 0.858. And is it leading or lagging? Lagging, because the angle is positive. We can rewrite it to be cosine of positive 30.96 degrees. That's why it is lagging. Okay? Any questions? Yes.
Is it more common for things to be leading or lagging one way or the other, just like out in the real world?
Actually, this is a great question. So we see that lagging many times. So is it common to see lagging? Yes. So that's how I'm gonna discuss in the next topic, which is power factor correction. What are the most loads in industry? What do you think, guys? What's the loads in industry? If you are in the factory, what are the common loads? Is it the lights? The lights, yes, we have a lot of lights, but the lights consuming low energy or lower energy with respect to the other machines. So motors, right? So these motors, the equivalent circuit of the motors are a combination between resistors and inductors. This is the equivalent circuit. We will discuss this in the next few lectures. So the motors can be modeled as inductors and resistors. These inductors are leading or lagging. When we talk about inductors, lagging. That's why in real life, most of our applications are lagging. So when we have in a certain factory a large amount of motors, a large amount of lagging, this will make the power factor poor, will make it low and low and low. So sometimes you can see the power factor is about 0.6 or 60%. So this is not, this will affect on the grade, and this will not be cheap. So what should I do? I need to improve this, or I need to make it higher than this. So let's assume in a certain factory that I need, or in a certain machine, I need 4 kilowatts as a power requirement. And my power factor was 75%. So when I have, let me assume I need 3 kilowatts. Okay, I'm sorry. I need 3 kilowatts, and my power factor is 0.75. So the apparent power is needed to satisfy this, which is 4 kilowatts. So 4 times 0.7 will be 3. How about if my power factor is 50%? Then I need 6 kilovolt ampere to satisfy the 3 kilowatts. In order to get 3 kilowatts, 4 times 0.7, I can get 3, while 6 times 0.5, which is 3. So for the same amount of energy that I need 3 kilowatts, in some situations I need 4 kilovolt ampere, some situations I need 6 kilovolt ampere. So if I need 6 kilovolt ampere, this means I'm consuming higher energy, and I'm affecting this into the utility as well. I'm consuming higher energy, affecting on the utility, and this might make some problems, creating some problems, because I can use 6 to supply 3, or I can use 4 to supply 3. Which one is better? Using 4, of course. So when you have a poor power factor, then I'm spending more money. And actually, in real life, you will see in any factory, you will see 2 meters. 1 meter associated with real power, 1 meter is associated with reactive power, and measuring the power factor. So if the power factor was below a certain limit, then there should be a penalty for that factory. So they are measuring this, and if your power factor is going below a certain value, and you didn't do any action for a certain period of time, then there will be a penalty. And that penalty makes you paying more money to the utility, because it looks like they're giving you a ticket because you didn't improve your power factor, because this is affecting on our system. So what you need to do I need to keep paying the penalty? No. So you need to improve this. How to improve this? By inserting some devices that improving the power factor. Most of our loads are inductor, and most likely the power factor is poor, which is for example 0.6 lagging. So we need to make it higher. How can I cancel the effect of the inductor? Capacitor. Because we know the inductor has a positive impedance, the capacitor has a negative. So the inductor and the capacitor are the opposite of each other. So if I find a way to remove canceling the effect of the inductor by inserting a capacitor, and most likely of these capacitors will be inserted as, we call it shunt capacitor or parallel capacitors. Most likely in power engineering, any parallel device, we call it shunts. So shunt capacitor. So we are improving the power factor by creating something called shunt capacitor. Again, most likely the motors are a combination of resistors and inductors. So when this very high, I will get power factor poor. So to improve power factor, lower or try to lower L. How can I lower L? Add C. Add capacitor. So we are trying to cancel the effect of that. So this capacitor will be in parallel, or we call it shunt capacitor. And also, actually, in real life, it's called capacitor bank. Why it's called capacitor bank? Because this certain factory does not work every time with 100% full capacity. Sometimes this factory can work half capacity, 1/3 capacity, 2/3 capacity. So most likely this shunt capacitor in circuit analysis we donated by only one single capacitor. But most likely it's gonna be switch, capacitor switch, capacitor switch, capacitor, and so on. That's why it's called capacitor bank, because we have multi-capacitors. And we can turn on a certain capacitor if it's needed. So if it is at half capacity and we notice the power factor is 75, then let's turn on one capacitor. Then, the power factor 0.8. No, we still need, let's turn on another capacitor. Then 0.9, that's enough. We don't need to add all of these capacitors. Why I don't want to add all of these capacitors? Because this will make a negative impact to the grid. So I need to make my power factor within 90s. So there should be a limit depending on the criteria. There should be some criteria depending on the grid. There's an agreement with the utility and a certain factory. What's my power factor should be? And if I didn't do any action, there should be some device, or there should be something, some penalty on that. So what's this device looks like? How it's being added to the grid. This is an example of a real device that's used in a real factory. So this is the control switch panel here. So the single diagram will be like this. You will see here many lines because this system is a three-phase. We haven't discussed the three-phase yet, but you can just imagine, look at the line alone, standalone, or just each line is repeated 3 times. So we have a switch here, and we have a control units. So the electrical engineer work is how to program the control units and when this switch will be operating, when this switch will be operating, when to operate both, when this will be disconnected. Most likely when the load is high, the power factor getting low, then add certain capacitor. If the load is high or more, add another capacitor, and so on. If the load getting low, then disconnect them. Then at night, the factory is off, then turn off all of these capacitors. I don't need them. So they will be needed they will be switched on if needed. And actually also these capacitors are not only exist into a certain factory or in a factory in the industry, it also exists in the utility. Sometimes we have capacitors and we have something else called inductors, switching inductors. So these inductors or capacitors will be added if there is no load. Most likely when there is no load, we will get at night, for example, in some high voltages areas. So at night, the load is very low. Sometimes the voltage will be high, very high. So we need to reduce it to slow it down. Then we turn on the inductors. Sometimes when the load is very high, turn off these inductors. And the load still high, the demand is very high. Then we need to improve the utility. So we insert these capacitors. So some electrical substations have this amount of devices. This is not our purpose. Our target is to talk about the industry, but I'm just showing you that we are using capacitors and inductors in real life to improve the grid. So this device, it is being controlled to turn on or turn off depending on the demand. How is the power factor, or this is also the panel, how it looks like inside. So we need to improve it by switching on the capacitors if it's needed. Now let's go to worksheets number 11. Then we will see some examples associated with it. So worksheet number 11 talks about power factor. It's the same thing that I discussed, but here most likely it's talking about the theoretical part, not the practical parts. So how to calculate the power factor and how to do the power factor correction. So the second page give you the procedure how to do power factor correction. So the procedure, you need to make to correct the new power factor. So you need to have some information. You need to have the old power factor, the new power factor, my desired, and you need to have the voltages, or you need to know the voltages and the power associated with the system. So most likely you can see this kind of problem. Power factor correction example. Let's assume that you are in a certain factory, and in this factory They have 50 kilowatts with 0.8 power factor, and the voltage is 220 volts. Then they ask you, the utility says, your power factor of 0.8 is not enough. It's poor. You need to increase it by 95%. Otherwise, you will get a penalty. You have to pay. You have to pay us. You have to pay us maybe $100 or $1,000 per day, sometimes to 5,000, sometimes very large amounts. So your boss asks you, we need to increase this. Need to increase it from 0.8 to 95%. What do I need to do? So you should say, we need to add a shunt capacitor. Adding shunt capacitor will solve the problem because most likely our industries or our factory is lagging. Then it's lagging, has a lot of inductor. We need to add capacitors to cancel that effect. So he says, okay, what's the value that you need? Or what's the device you need? So you need to find the value. How can I find the value such that I can meet 95%? Someone can say, let's choose very large value. No, there's not enough. Because if you choose very large value, sometimes this might have a negative impact into the grade. So there should be a certain amount. As well as if you use very large value, it will be very costly. So let's find a way that economically good. How can I make it to 95%? That's my target. If I couldn't find a way, I would get fired. What should I do? Let's follow the procedure. According to the procedure in note sheets, there are 3 steps. Step number 1, for the old case, find QO. Solve for QO. Step number 2, find QN, Q new, which means QO, the reactive power for the original case. Then find the reactive power for the new case. Then step number 3, find the difference. This is the ratings that my device I need. Then the last thing, which is solve for C. That's how we find it. Just follow the procedures. So, according to these procedures, what should I do? Let's look. We have P original of the system is 50 kilowatts. We have the power factor 0.8. Again, 0.8 is not enough. We need to know, is it leading or lagging? So it's lagging. And we have, this is the power factor original. And we have V line, or V, the voltage is 220 angle 0 degrees. And the power factor in U that I need it to be 95%, 0.95, and of course lagging. So what should I do? Let's go to the procedure. Number 1, find the QO for the original case. So number 1, original case. So QO equals to PO times tan theta O. That's given in the worksheets. How can I find this? I know PO, but I don't know theta O. How can I find theta O? We can say theta O is actually cosine inverse of power factor original, right? So cosine inverse of 0.8, then it's going to be 36 something, 3687 degrees. Is it positive or negative?
Positive.
Positive. Why?
It's lagging.
It's lagging, right. So substitute the value. So it's going to be 50 kilowatts times 10 power 3, tan of 36.87 degrees. Then after substituting this into the calculator, it's going to be 37.5 times 10 power 3, and the units of the reactive power is what? Volt ampere reactive, or VAR. Okay? Now, according to the procedure, let's calculate for the new case. So Q new equal PO times tan theta nu. How can I find theta nu? In the same way that I find it theta original. So theta nu equal cosine inverse of power factor nu, which is cosine inverse of 0.95. What's the angle of that? Anybody found it?
18.19.
18.19. And it's going to be positive or negative? Positive because it's lagging. So most likely, lagging. So most likely the default is positive. Unless when you see leading, then think about that side, which will be negative. So PO is 50 times 10 power 3 tan of 1890. Then after substituting this into the calculator, it's going to be 16.43 kilovar. I'm sorry, 16.3 times 10 power 3 var, or in other words, 16.43 kilovar. I think you should know kilo, which is times 10 power 3. So the third step, what's the third step? Find the difference. So we will say QC is the absolute of the difference, delta Q, which will be the absolute value of Q nu minus QC. So it's going to be Q nu 16.43 kilovar minus 37.5 kilovar. Then it's going to be 21.07 kilovar. This is the Q of the capacitor. Okay? The last step, how to find C, which is step number 4. We'll say that C equal QC over VC squared times omega. QC, we already calculated it here. How about omega? Omega equal to what?
Oh.
2 pi times F, right? Omega equal 2 pi times F. Is the frequency given? No. So what's the frequency? 60 hertz. So 2 pi times 60. Then it will be 377 radian per second. How about VC? What's the value of VC? The value of the voltage given 220. And since there is no bar, don't put the angle. There is no bar, just the magnitude. Okay? Then C will be QC, which is 21.07 times 10 power 3 divided by 220 square times 377. Then the final answer will be 1.15 times 10 power negative 3 farad, or we used to write it in milli or micro, so just make it shortcut, which is 1.15 millifarad. Okay, any questions? Any questions how we found it? Just follow the procedures and substitute the values. Then you can go to your boss and say, I need 1.15 millifarad to solve the problem. Then problem solved. Then you can save your job. Okay? Yes.
What is that squared? It's QC over what's
VC.
VC squared times omega. V sub C or V squared. So sub C because this is the voltage of the capacitor. Or the voltage is given, that's fine. Any other questions? So this is the concept of power factor correction. Let's see some examples. Let me give you some time to write. I will start an example from the supplemental problem set. I want to start with problem 48 first, then go to another problem.
Oh, that's just
Okay? So problem 48 from the supplemental problem sets. A load operates at 20 kilowatts with a lagging power factor of 0.8. The load voltage is 220 and the impedance line 0.09 plus j 0.3. Determine the source voltage and power factor of the source. Now this AC problem with different types, which is we need to know the power factor. So how can we solve these kind of problems? The first step, model the problem. We have a load, we have a source, and we have a transmission line. Problem 48. We have a load, or we have a load, then we have a transmission line, and we have a source. Right? Right? Yes. So now we can model it by saying the voltage source is being modeled as this shape, this voltage source. And a transmission line, I'm going to call it Z line. Then we have a load. So I'm going to write plus minus load. The given information, which is we have the load operates as 20 kilowatts. And we have the power factor of the load 0.8 and lagging. You need to know how to convert this to this. And what else? We have the voltage of the load, which is, here is positive, negative. V load equal 220 angle 0 degrees. We have the transmission line impedance, which is 0.09 plus j 0.3 ohms. And I need to know V source. How can I know V source? So just try to convert the written words to be equivalent circuits analysis. This is very important. How can I know V source? Someone can say, I can use KVL. Right? KVL, negative V source plus V line plus V load equal to 0, right? What's V line? Is I times Z. Negative V source, or we can say V source will be V line plus V load, which will be I times Z line plus V load. Right? Do I know V load? Yes, it's given. Do I know Z load, Z line? Yes, it's given. Do I know I? No, I don't know I. Right? How to find I? Now my problem is how to find I. How can I find the currents? How to find I? Use the available information. Use the available load information. I have P, I have power factor, I have V. P load equal 20 times 10 power 3 watts. Power factor equal 0.8 lag. So we can find theta by saying theta cosine inverse of power factor, which is cosine inverse of 0.8. Then it's going to be 36.9 degrees and should be positive because it's lagging. Right? So what else? I know P, I know theta. I can say S is actually equal to P load over power factor. Then it's going to be 20 times 10 power 3 over 0.8. Then the answer will be 25 times 10 power 3 volt ampere. Then I can know S bar, which will be S angle theta. So it's going to be 25 times 10 power 3 angle 36.9 degrees volt ampere. So what else? How can I find I? The first step, you need to know, use the available information to know the complex power. And what's the value? What's the formula of the complex power? S bar equal V bar times I bar conjugate. I know V, I know S, so I can find I. So just recall the DC circuit analysis. I know P, I know V, you can find I. Is that right? So S bar equal to V bar times I bar conjugates. Therefore, we can say I bar conjugate will be S bar over V bar. Or in other words, I can say I will be S over V bar all conjugates. Okay? You need to know this procedure. We will apply it a lot. The same procedure, exactly the same procedure. We will apply it a lot. Which is, first, how to find the complex power from the given load information, and how to find the currents from the complex power. We will use it not only in this lecture, we'll use it in next lectures, more and more. We'll go to the applications. When we go to the electrical machines, we will use it. When we go to the transformers, we will use it. So you need to be aware how to find this. When we go to the three-phase analysis, we will use it as well. So I equal S bar over V bar conjugates. So how to find these values? So substitute them. So S equal 25 times 10 power 3 angle 36.9 degrees divided by V, which is given 220 angle 0. Don't forget the bar. So don't forget the conjugate. So substitute it into the calculator. We will have I load will be, when you substitute this, 113.636 angle 36.9 degrees conjugates. Again, don't forget these conjugates. Left the conjugate at the end. One of the common mistakes, a lot of people missing the conjugate, then they get incorrect results. So how to apply the conjugates? Just reverse the sign of the angle. Okay? And the unit here is ampere. Understood? Does everyone get it? Any questions? Now, this is I load. Let's recall the problem here. We said we didn't know I. We already calculated here. So substitute this. Then V source will be I, which is 113.636 angle negative 36.9 degrees times Z, which is 0.09 plus J 0.3 plus V load 220 angle 0. Okay? After substituting this, then V source will be 249.5 angle 4.859 degrees volts. This is the first unknown. Any questions? The second unknown, power factor of the source. Power factor of the source equal to what? Cosine alpha source minus beta source. So what's the angle? What's the alpha? What's alpha? What's beta? Here. So it will be cosine of alpha 4.859 minus beta, which is beta here negative 36.9. Then the answer will be 0.75. Is it leading or lagging?
Lagging.
Lagging. Why? Because negative will be positive, so the sign will be positive. So lagging. Lag because theta is positive, or alpha minus beta is larger than 0. That's Any questions? So that's how we find or how we solve the problems associated with the power factor analysis. So I encourage you to see also problem, I think problem 49. Try it at home. And problem 50 as well. Try it at home. 49 and 50. So you will find their answers on Canvas. So you don't need to worry about what if my answer is incorrect? What if I didn't get it? So try it after today's lecture. Try it without looking at the answers. Then you can see the detailed answers on Canvas and explain and see. Let's see another example. Supplemental problem set related to power factor correction, which is problem 55. An industrial plant is operating at 2,400 volts, consumes 100 kilovolt ampere at power factor 88. And they need it to make it unity power factor. In real life, they don't want it to make it unity. In real life, it should be in 90s. But let's assume that we need to make a unity power factor. How can I solve the circuit? How can I solve this problem? Let's write the available information. We have V load equal 2,400 angle 0. And we have SO equal 100 kilovolt ampere. We have power factor original 0.88 lag, and power factor new, we need to make it 1. How can I do my analysis? So let's go back to the worksheets. Power factor correction here. We have SO, we need to find PO, which is SO times power factor O. Then PO equal SO times power factor O, which will be 100 times 10 power 3 times 0.88, which will be 88 times 10 power 3 watts. Okay? The second step, let's go to new original case. Original case. So original case, PO equal to SO times power factor. I'm sorry, we already did this. We need to know QO. QO, which is PO times theta O. Okay? PO is given, but I don't know theta O. How can I find theta O? Theta O equal to cosine inverse of power factor original, which is cosine inverse of 0.88. Then it's going to be 28.358. Is it positive or negative? Positive because it's lagging. Then substitute it. So it's going to be 88 times 10 power 3 times tan of 28.358 degrees. Then the answer will be 47.5 times 10 power 3 var, or in other words 47.5 kilovar. Okay? Is that clear? Then the new case. The same scenario, Q nu equal PO times tan theta nu. So theta nu equal cosine inverse of power factor nu. Then it's going to be cosine inverse of 1. So cosine inverse of 1 is going to be 0. Then Q nu will be PO, or 88 times 10 power 3 times tan 0. What's the tan of 0? 0. So Q nu will be 0. Okay? Then, third step, QC will be the absolute value of delta Q, which will be the absolute value of Q nu minus QC, or Q nu minus QO, when it's going to be 0 minus 47.5, then it's going to be 47.5 kilovar. And the last step, C, will be QC divided by V squared times omega. So omega is not given, then the default is f equals 60 hertz, then omega equal 2 pi times f, which will be 377. Then it's going to be QC 47.5 times 10 power 3 divided by V square. V is given 2,400 square times omega 377. Then by substituting this, it will be 21.87 times 10 power negative 6 farad. And since we don't like this exponent, we try to make it easy. So it's going to be 28.87 microfarad. This is the needed capacitance to make it unity power factor. Any questions? Again, we follow the procedure that's written here. So you can write this in your note sheets. Even for the quiz, you can write this in your note sheet. Any questions? Okay, so that's all of what you need to know about the power factor correction. Now, I want to discuss introduction, or the other part of the lecture,